I'm going to talk about sort of the whole area of driverless cars or alternatives to that. And another alternative title for my talk is Smart Cars or Smart Roads. And I pose this as a question. Okay, so I want to start with a bit of history because everybody thinks that self-driving cars were invented like 10 years ago. That's not really true. So I'm somebody who's been in the field of artificial intelligence since the early 1980s. So I want to remind you of what people could do back in the 1980s. So it started out as work on little mobile robots. So up on the slide picture, you see what's called the Stanford cart and what's called Shaky. And then in the 1980s, there was a professor called Ernst Dickmanns in Germany who started a big self-driving car project. And this required a major boldness because think about the computing available then. So we always talk about Moore's law going forward, but to appreciate the situation in 1985, let's say, which is 35 years ago, you have to think of Moore's law backwards, right? So if every 5 years computing goes up by a factor of 10, that means that at that time computing was like 10 to the 7 less than what we have today. But Dickmann's insight was that to drive a car on a road, what you need to do is a few simple things rather than understand the entire scene. And he focused on freeway driving. And he was able to do it with like an Intel processor or what was available, Intel microprocessor available in the 1980s. And he showed that what you had to do was to drive the car was to know where the lanes were to the left and right. You needed to know the distance to the car in front of you. And then with that, you converted it into a control problem. And with that basic idea and control theory, he demonstrated in the 80s cars driving on German autobahns. And these are freeways which go much faster than say, let's say in the Europe. Okay, and at 80s and 90s, there were several car driving projects. Okay, and I have a slide here which shows some of that. So CMU was another major center. And there was an approach based on neural networks called the NavLab. And then I have some other slides here of projects which are in the early 90s. Then the US federal government sponsored a big program of research which was aimed at, okay, can we automate highways? Can we have self-driving cars? And there were ideas such as, if we have self-driving cars, then we could put them in a platoon. So effectively, you could assemble a bunch of cars together and make a train out of it, if you will. And that way, the capacity of the freeway is enhanced. So here, this slide shows this paper that we wrote at that time. So my group, back in the late 90s, we had a project on this, and we showed a self-driving car using stereo vision and so on and so forth. So really, there were successful projects in self-driving cars back in the 90s. Okay, then I want to, for context, I want to tell you about what I said when in the current hype on self-driving cars. So I was interviewed by the New York Times 4 years ago. So this is, if you can read this, the date here, it says September 19, 2016 is when this interview was. And I, at that time, tried to be slightly, hype canceling. I said, look, everybody thinks that we'll have self-driving cars the next year, and this is 2016, but this is not true. And I did not have faith in the technology for full automation of self-driving cars. And the quote here is that, knowing what I know about computer vision, I wouldn't take my hands off the steering wheel. And that was 2016. That was 4 years ago, and people were predicting, oh yes, in 2016, and we'll have this, and 2017 we'll have this, and what's called level 5 autonomy is there 2 years from now. And there had been major investment in, of course, in Google in the form of Waymo, Uber, Tesla, and there are maybe like 100 startups all aimed at capturing the self-driving car market. And so now I have to explain why I, who have been in this technology, I mean, back at like 20 years ago, more than 20 years ago, I had a self-driving car project. Why was I being pessimistic rather than optimistic about the success of this technology? And I want to note that generally speaking, I'm not a pessimist. I think the advances that we have had in various fields of computer vision, robotics, machine learning have been truly amazing. And for example, the technology which enables speech recognition, or the technology which enables translation from one language to the other, or technology which enables us to recognize faces. I mean, that stuff has been really impressive. But why was I being pessimistic about self-driving cars? And I'm still pessimistic today. The first reason is that we need a very low error rate. Okay, and this you can calculate by trying to figure out if you have so many hours of driving, then what's the fatality rate? What's the rate at which there will be accidents? And so for human drivers, these are numbers from the US, it's around one fatality per million hours of driving. So there's something like 35, 40,000 people who die in a year in the US due to car accidents and so forth. And if you want to replace this technology by an automated technology, you want to have a much lower fatality rate. And Amnon Shashua of Mobileye, this is a leading company in terms of computer vision technology for driving cars. And his estimate is that the fatality rate should be less than one per billion hours of driving. Okay, so that's what we have to achieve. Okay, the second remark is that the technology which is being used is machine learning. And the problem with machine learning is that the error rate, as we try to squeeze it down, it gets harder and harder. So trying to get to, say, a 10% error rate might be quite easy. Trying to get to 1% error rate, okay, you have to put in maybe 10 times as much data. Then we want to reduce it to 0.1% error rate, and so on and so forth. Every stage is very, very hard. So that is the challenge. And if you think about this problem, we get numbers which are simply not feasible. If we just use these ideas and we want to have an error rate which is less than 1 per billion hours of driving. It's actually worse than that. The problem is worse than that because getting perception to be error-free is only half the problem. The rest of the problem is about control or decision making. And again, there are certain settings of the problem which are relatively easy, which is driving on the freeway where everyone is obeying lane rules. But suppose you're driving in urban streets with mixed traffic, the number of strange cases that can happen, what people would call edge cases or corner cases, are hopelessly many. And just trying to program them in case by case is sort of not a feasible strategy. So I believe that fully automated cars, what people call level 5 autonomy, is not in the near future. And you don't have to just take my word for this. This is the chairman of the National Transportation Safety Board in February 2020. And this is his statement. This was in the context of sort of investigation of, there was an Uber crash which led to someone dying. And after that inquiry report, this is one of the statements from the National Transportation Safety Board, which is that there is no vehicle currently available to the US consumer which is self-driving. And what we do have are advanced driver assistance systems. So now that I have stated something negative, I start with this negative result, which is sort of bad because a technologist always wants to be positive and optimist. Let me try to say what we can do. And I think it's good to know what we can do. So first of all, I think driver assistance systems add value. So a lot of the research which has been going on in the area of self-driving cars can be useful even if the car is not fully self-driving. But what is being computed by the system is used to provide assistance to the driver. For example, we could have early warning systems. So a pedestrian is crossing the road, you could detect that and provide a warning to the driver. The driver might be driving way too close to the car in front of him or her. You could provide a warning to that. You might be falling off, pushing off too much to the one side or the other. You could provide a warning for that. So if you have a good user interface and you provide a warning system, you could save many lives and you could reduce the accident rate. This is a subtle problem because we need to provide input in a form that is useful to the driver whose attention is a scarce resource. But I think driver assistance systems are of great value, and research on self-driving cars should continue. And maybe a decade from now, we might have something which can be used widely. And even before that, we could have specialized settings in which the technology could be useful. Okay, what I do want to say is what we should be doing, what we should really be investing in much more, which is what are called advanced traffic management systems. So the basic idea is to view the traffic system as a system, okay? It's a control system. And we all know about control systems. So control system in your house, you have a thermostat, and then you adjust whether you have the furnace or the air conditioning so as to maintain the desired temperature. So you need sensing and you need control. So what we should think about with respect to the traffic system in a city is that we can have sensors everywhere. For example, there could be cameras mounted at traffic lights. There could be cameras mounted on the roadside. And of course, there is a ubiquitous sensor that is available, which is the location signals from driver cell phones. So with these, we can essentially have a sense of the flow of traffic at a very microscopic scale at every lane, at every location. And that is what the sensing does. And then what you can do is control. And these are examples of some of the kind of control we could have. We could have, and these are examples from the US context, but these are relevant around the world. For example, if you have a freeway, we have this observation from traffic engineers for quite a few decades now, that traffic can basically flow at 2,200 vehicles per lane per hour. That's the best you can do. It's because of human reaction time. When people drive, they're going to have a certain distance between two cars going at their, let's say, 60 miles per hour. So if you put more traffic on the road, then the capacity of the road actually decreases. So what you want to do is to control access to the freeway so that the freeway is operating at maximum capacity. So that's one idea. Second idea is that if you don't do traffic lights just based on a local signal of how many cars are waiting, the length of the queue, or just fixed time or whatever, you look at the pattern spatially around the neighborhood and you solve an optimization problem. Third idea, this is essentially one about design, that when you design, say, a traffic intersection, what you want to do is to look at how it is being used and what are the flow patterns in this particular place. And then we can learn from near accidents. So we don't just have to get the statistics when there's actually a crash or a pedestrian has been hit. We can learn from near accidents, and a camera system will detect those. And the next example that I have is that we could have pricing for congestion control. If we choose to control traffic and use that as a way to get efficiency, we can do that. So this is my concluding slide. I think this is not as fancy and as every car is self-driving, but it is really very, very useful for society, and it can be done today if we invest in it. The challenge here is that there isn't an incentive for individual car manufacturers. They all have an incentive to build self-driving cars because then people will buy those cars and they will make money off that. But improving the transportation system as a whole to make it more efficient is not something for which any individual car manufacturer has an incentive. So this is why it's been neglected. So this falls in the domain of this is the government's job, local government, city government, state government, federal government. But the gains are immense. So if you think about the amount of time that people spent in their cars, and suppose you made the system 10% more efficient, and then they would spend 10% less time on the road. Well, just think of the value of all of people's time if you could save 10% of the time spent in traffic. Think of the benefits you get in reduced usage of oil or reduction in pollution. So the moral is this is very important. This is very doable. We have a lot of the technology that would be necessary, but this is a role for government. And I conclude by noting that smart cars are great, but we are not likely to see level 5 autonomy, fully self-driving cars in the near future. However, investing in smart roads could yield major societal benefits both in the near and long term. Thank you very much for your attention.